Alright, in this lecture we want to discuss vector products. There are basically two forms of vector multiplication. The inner product, also known as the dot product, and the outer product, also known as the cross product. So the inner product is basically, you can ignore a lot of this stuff, it's basically a multiplication of two vectors that really gives the projection of one vector onto the other, and so the outcome is a scalar. So we define this as A dot B, also read dot product. I have no idea why in your textbook in this equation they have this little G here. I'm guessing something went wrong somehow in their symbolism of doing the dot product. But this should be a dot notation, just like what you see down here and up here. So A dot B is the magnitude of A times the magnitude of B times the cosine of gamma, where gamma is the angle between them. Assuming gamma is between 0 and pi, and A is not equal to 0, and B is not equal to 0. A dot B is equal to 0 if either A or B is equal to 0. So the angle is measured right where the initial points coincide. And so if we want to calculate the dot product, we take the product of the coefficients of the x vector, the product of the coefficients of the y component, and the product of the coefficients of the z component. This illustrates graphically what you just saw. In this case, when this angle gamma is greater than 0, or when this angle gamma is less than 90, then A dot B will yield a positive number because basically you're calculating the projection of A onto B. When gamma is 90 degrees, so A and B are at right angles, then the dot product is 0. And this is important because this is one of the ways we define orthogonality, meaning that there is no projection here. If we were to project A down onto B, we would get a projection of 0. Now this is just intuitively obvious in 2 dimensions and sometimes even in 3 dimensions, but you remember earlier I talked about multidimensional data sets or multidimensional vectors where you have dimensions that are higher than just the spatial dimension. So the dot product is an important way to know if there's commonality or if all of your vectors are orthogonal. And then finally, if gamma is greater than 90 but less than 180, the dot product is less than 0. So once again, here's the discussion of orthogonality. A vector A is said to be orthogonal to a vector B if A dot B is equal to 0, and obviously this would mean that they would both have a non-zero length. Okay, so the inner product of two non-zero vectors is 0 if and only if these vectors are perpendicular, and that is the orthogonality criterion. And as I said, this can be applied to even higher than spatial dimensions. Length and angle. So the magnitude of A is defined as the square root of A dot A. So we can do some back calculating that the cosine of the angle gamma is A dot B over the magnitude of A times the magnitude of B. So in that way, by finding the dot product between two vectors as well as their magnitudes, we can calculate the angle between them. And once again, I apologize for this stupid little G here. That should be a dot, not a G. Some kind of issue with your textbook. So from the definition, you can see that the inner product has the following properties, and this is just the property of linearity, the property of symmetry. So A dot B is equal to B dot A, and A dot A has to be greater than or equal to 0 unless A is 0. So once again, this should all be reviewed. We obey the distributive property that A plus B in parentheses dotted with C is equal to A dot C plus B dot C. And because the cosine of gamma is less than or equal to 1, then basically the magnitude of A dot B has got to be less than the magnitude of A times the magnitude of B. This is known as the Cauchy-Schwarz inequality, sometimes known as the Schwarz inequality, and it's a very important property because basically it leads to the triangle inequality, which says that the magnitude of A plus B is less than the magnitude of A plus the magnitude of B. So this says that, One side of a triangle has to be shorter than the other two sides summed together, otherwise it's not a triangle. And then you can also show the parallelogram equality, which is less commonly used and can come from the triangle inequality. So basically, this is what I was discussing earlier, that really what the dot product does is it gives you a projection of one vector onto another. If you want to find the length of that projection, then you basically can take the magnitude of A, multiply it by the cosine of gamma, and that gives you the length of the projection of A onto B. The length of the projection of A onto B gives you some idea of how far from orthogonal the two vectors are. And this is important in things like principal components analysis and transformations that gets you to a principal components kind of description of a set of data. All right, so if we multiply this by absolute value b over absolute value b, then in the numerator you would get a dot b over the absolute value of b. And so if b is a unit vector, which is just to get a direction, and that's often done as well in multivariable data sets, then this projection is just a dot b. But if you want the projection and you do not have unit vectors, then you do need to divide by the magnitude of b so that you're getting the true projection and not magnitudes. And here's an illustration of that. And so A will project onto B, but B will also project onto A, and just depending on which one you're interested in this case, if you wanted the projection of B onto A, then you would take the magnitude of B times the cosine of gamma. And then this is just a little bit about an orthonormal basis set. Basically, an orthonormal basis set for three-dimensional space consists of three orthogonal unit vectors. So our I hat, j hat, k hat is definitely an orthonormal basis in the rectangular or Cartesian coordinate system. There are orthonormal vectors and standard bases that you can find for any given coordinate system. And you can also find an orthonormal basis set for multidimensional data that goes beyond 3D. The other kind of product is the cross product. The cross product is known as the outer product. So the vector product A cross B is basically the magnitude of A times the magnitude of B times the sine of the angle between them. In this case, it's pretty obvious that orthogonal vectors will have a zero cross product. Orthogonal vectors will not have a zero cross product. They'll have a zero dot product. Parallel vectors will have a zero cross product because a unit vector crossed with itself gives you 0 because the angle gamma would be 0 and the sine of 0 is 0. So the cross product kind of measures the amount of rotation that you undergo in going from vector A to vector B. So we will skip this because it doesn't make a lot of sense, or it's not really particularly useful. Some people do refer to this as the outer product. The direction of the cross product vector. So the output is a vector, the output of the cross product, and the direction is that it must be perpendicular to both A and B. So if you take your right hand and you place it in the direction of vector A and you move it toward vector B, the direction in which your thumb points is the direction of the cross product vector. So if we have some vector A defined by A1, A2, A3, and vector B defined by B1, B2, B3, then the cross product has the following components. You can get this from a matrix manipulation as well, where you create a matrix that has IJK in the first row, A1, A2, A3 in the second row, B1, B2, B3 in the third row, and you calculate the determinant of that. If you do that, then you will get this expression. So we already discussed that we use the right-hand rule in order to find the direction of the vector v. We also discussed that basically a cross product is looking at sort of the degree of rotation that occurs in going from the direction of A to the direction of B. So obviously the closer A and B are to being parallel, the smaller the cross product will be, whereas if A and B are perpendicular to one another, that's going to maximize the cross product. Here's an example of what the book has been referring to as right-handed triple and what I've been referring to as the right-hand rule, just illustrating that if you go from A to B, this is the direction of the cross product. So the system is called right-handed if the unit vectors I hat, j hat, and k hat are in positive directions of the x, y, and z axis. So this figure on the left illustrates a right-handed coordinate system. It is possible to have a left-handed coordinate system that reverses and inverts everything. So I have never in my over 30 years of experience in teaching and practicing in science and engineering encountered a left-handed coordinate system. So we will just ignore this half of the figure. Here are some vector products or cross products of standard basis vectors for rectangular coordinate systems. So you have I cross j is equal to k. Notice if you reverse the direction of the cross product, you will get negative k. Once again, this is unlike the dot product, the vector product is order dependent. So I cross j or a cross b is not equal to b cross a. There will be a change in the sign, SIGN, of the result. So some general properties, scalar multiplication can be done on either term or after the cross product on both terms. The cross product is distributive with respect to addition, but it is not commutative with respect to multiplication. So in other words, b cross a is not equal to a cross b, b cross a is equal to minus a cross b. The mathematical term for this is anti-commutative. And it's not associative in general. So A crossed with B cross C is not equal to A cross B crossed with C. So you cannot leave your parentheses out. You must know the order of the cross product. Certain products of vectors having three or more factors can occur in some applications. The most important is called the scalar triple product, which is A dotted with B cross C. It's a mixed product of three vectors. It does turn out to be a scalar because B cross C will be a vector, and then A dotted with that resulting vector ends up giving you a scalar. A lot of times the scalar triple product is expressed using a determinant. Here is how that's done. A dotted with B cross C. Here is the B cross C. Element 1, element 2, and element 3, and then that's just going to be, that determinant factor is just going to be multiplied by A1, A2, and A3 respectively. So that's illustrated up here that if we let B cross C equal V, then A dot V is illustrated here. And this is the one that I actually like a little more, which is where you show basically row 1, row 2, row 3. This is once again for the triple crop product, A dotted with B cross C. So you put A in the first row, B in the second row, C in the third row, and the ordering on that is important. So there are some properties of scalar triple products. We won't prove these. Once again, I think you should have seen these. But if you haven't, just to review you, and the main thing that we want to talk about is that A cross B dot C is equal to A dot B cross C. So it has this property that can be sometimes useful. And then we also want to talk about linear independence. So three vectors in real number space are linearly independent if and only if their scalar triple product is not 0. All right. Dot multiplication is commutative, so it doesn't matter if you do the cross product first and then the dot. It doesn't matter which side C is in, so it's the same no matter how that is. And then we will skip over this because we're not really concerned with spatial properties. We can say that three non-zero vectors whose initial points coincide are linearly independent if and only if the vectors do not lie in the same plane or on the same straight line. So that's a consequence of linear independence, and once again, that can go beyond 3 dimensions into multidimensional space. All right, so that concludes the concept of vector product, and the next lecture will cover vector and scalar functions and their fields, and we will look at derivatives.